In this video, we want to look at applications of sets. We'll start off here with what is called the Inclusion-Exclusion Principle. It says that counting problems occur in many areas of applied mathematics. To solve these counting problems, we often make use of a Venn diagram and the Inclusion-Exclusion Principle, which will be presented in this section. Recall our notation here that N of A represents the number of elements in a set, right? And that set is A. So what about our number of elements for when we look at our unionizing of two sets? That is, the number of elements for A union B must be considered as N of A plus N of B minus N of A intersect B. Let's think about what this means here. This means that if you are adding together the number of elements in set A and set B, you must subtract the intersection because there may be elements contained in both A and B. So think about if set A has 5 elements and set B has 3 elements. What if 2 of those elements can be found in both set A and B? That is, we have added those 2 elements twice. That is the inclusion-exclusion principle, and that when you include a number of items twice, you must then exclude that number at least the one time. In this case here, the number of elements for A added to the number of elements for B minus the number of elements that are found in both A and B. What must be true of the finite sets A and B if the number of elements from A or B is equal to the number of elements of A plus the number of elements for B? Well, quite simply put, if the two sets are disjoint sets, meaning that they have no overlap, meaning that there is not an element in A that's found in B, well, the principle tells us then take the number of elements in A and add it to the number of elements in B. You don't have to worry about subtracting the intersection because there is no overlap. There are no numbers found in both elements, or rather both sets A and B. So when the two sets are disjoint, you simply add the 2 number of elements together. If the 2 sets happen to overlap, in other words, there is an intersection, well, this means that you must subtract out however many are in the intersection because that number is included for both N of A and N of B. We have an example here that helps us understand the inclusion-exclusion principle a little bit better. It says we have a high school that has 80 athletes who play basketball, 60 athletes who play soccer, and 24 athletes who play both basketball and soccer. So think intersect. How many athletes play either basketball or soccer? So they want to know how many play either basketball or soccer. So they want to know which of those 4 numbers above. Well, it's the one on the left, right? N of A union B. If you think about this here, we're going to let the basketball be denoted as capital B, soccer as capital S, and therefore the number of people that play basketball, 80, is going to be N of B. Go to the full screen. The number of individuals who play soccer are 60. The number of individuals that play both sports, that is basketball and soccer, is 24. They want to know how many athletes play either or, right? Either basketball or soccer. They want to know this one. So in this application, they're giving us 3 known values, and we're solving for the unknown. The last sentence is a question. That's the question that's being answered. How many? And this notation represents the number of elements, or how many play either basketball or soccer. So we're just going to use the formula that says to find the either or scenario, we will take our formula here, add the number of basketball players to the number of soccer players, and then subtract the overlap. Subtract those that play basketball and soccer, because when you think about it, those 24 individuals here are being accounted for within this 80 and within this 60. So the 24 is being accounted for twice. We need to take it out one time. We need to take it out one time. 80 plus 60, 140. 140 minus 24, well, 140 minus 20 is 120. 120 minus 4 is 116. So the number of individuals that play either basketball or soccer, 116 individuals. Let's look at our next example here. We have on our exercise, given n of A is 785, n of B is 162, and n of A or B is 852, find n of A and B. Once again, given three of the numbers, find the unknown. Look at the formula here. It wants us to now find that fourth number, right? We're given the first three. So if we were to fill that in, let me do some erasing here. I'll change the notation to what the problem suggests. It says n of A, 785. It says here n of B is 162. It says here that n of AUB is equal to 852. So this is the one that we want to find, right? We want to find the number of elements that are in A intersect B. And look at the formula given to us here. Right? We want to find that last number. In this case here, the first number on the left of the equal sign, right, is going to be 852. 852 is equal to 785 plus 162 minus the number of elements that are in the intersection, right? We can take that notation and write it here, or for a nice linear equation, right? If we don't know a number, right, something that's unknown, remember that according to algebra, we have a definition. A quantity or a number that's unknown is a variable. Popular variable is x. So I'm going to go to my calculator over here because it's going to be efficient for me. 785 plus 162 is 947. So 947 minus some number is 852. So it would benefit me to know what number do I subtract from 947 to get 852? Well, if I subtract these two numbers, I'm going to find it. 947 minus 852 is 95. In other words, if I subtract this number over here, I get negative 95, I get negative x, multiply negatives on each side, x is 95. So here, we can now determine that n of A intersect B is 95. And there we have it. Another example, given n of L is equal to 780, n of M is equal to 240, and n of L intersect M is 50. Find n of L or M. All right, L union M. Once again, using the formula, I'm going to do some erasing here. Using the notation for L and M, just replace the A and B notation that we have given at the beginning. We have here that 780 plus 240 minus the intersection, minus 50, is now going to give us n of L union M. 780 plus 240 is 1020 minus 50 is 970. There you have it. 970 is the number of elements that are found in the union, L union M. Number 15, given n of A, given the union, given the intersection, find the number of elements for B. N of A, 1500, plus n of B, well, that's what we want to know. That's the one that we don't know. Subtract the intersection, subtract 310. And this equals the number that's at the union, 2,250. An example here, right, that we can relate back to our early algebra days, pre-algebra. In order to solve for this unknown here, I can take 1,500, subtract 310. 1,500 minus 310 is going to be 1,190. And that's positive, so we'll add that to the sum for n of B. and this equals 2,250. All right, what number do we add to 1190? In order to get 2,250, we want to find that difference in between, that distance. So 2,250 minus 1,190 is 1,060. So that is our number of elements for set B. Another example, given n of A is 640, n of B is 280. The number of elements at the union is 765. Find the number of elements at the intersection. Same setup, n of A, 640, plus number of elements for B, 280. Subtract the number of elements that are at the intersection. That's what we're trying to find. So that's our unknown. Again, if you want to just use the variable x here, 640 plus 280 minus x, that's fine as well. This equals the number of elements for the union, 765. So we'll start by adding 640 and 280. 640 plus 280 is 920. 920 minus the number of elements at the intersection will bring us down to 765. So what number am I subtracting? What's that number between 920 and 765? Well, I can subtract to find it. 920 minus 765 is 155. So when we have a formula that is relating four numbers together, well, when given three of those numbers, we can always find the fourth unknown just by working with our inclusion-exclusion principle formula. We have an application involving a movie company. The movie company is making plans for future movies it wishes to produce. The company has done a random survey of 1,000 people. The results of the survey are shown below. We have the information listed, and below we have the questions of the people surveyed. How many people like action adventures but not comedies? How many people like comedies but not action adventures? How many people do not like either of these types of movies? Let's start with part A here. How many people like action adventures but not comedies? Well, action adventure says there's 695 people that like it, but they don't want it to overlap with comedies, right? If we think about the regions for this, action adventures is region 1 and 2, but 1 is also in the comedies, and we don't want comedy, so we don't want 1. Part A is 515. Part B, how many people like comedies but not action adventures? Well, again, for comedy, there are 340 people that like comedy, as the information above tells us. But we don't want those that overlap with action adventures. Again, taking away the 180 in the middle, we see that the number of people that like comedies but not action adventure is 160. Part C, how many people do not like either of these types of movies? Well, they don't like action adventures, they don't like comedies. It says above, right? There are 180 people that like both action adventures and comedy. But how many do not like either of the two? Well, we're not talking about anything in the circle. Part C, we're talking about that number that lives outside of the circle. That's 145. For part C, 145 people do not like either of these types of movies. Our next exercise. The athletic director of a school has surveyed 200 students. The survey results are shown below. Of the students surveyed, how many students like volleyball but not basketball? How many students like basketball but not volleyball? And how many students do not like either of these sports? So without the information given for that last region, once again, right, if we wanted to create our Venn diagram, we're only given volleyball and basketball. So there's only going to be two circles. To the left, volleyball, V. To the right, basketball. And on the outside, the universal. In the middle, 85 students like both. So 85 goes in the middle. Now, 140 does not go to the left, right? Because 85 of the 140 are already there. So what's the remaining, right? 140 minus 85, or 55. So now we see the grand total of 140 are in the volleyball. Likewise, for basketball, there's 120, but 85 of them are already accounted for. Right? That's why in the formula before we had to subtract the overlap, subtract the intersection, because 85 is going to be included in this circle, and 85 is going to be included over here. 120 minus 85 is 35. Now keep in mind, right, that 200 students were surveyed. And up to this point, how many do we have accounted for? Well, let's kind of cross the board, right? 55 plus 85 is 140. 140 plus 35 is 175. So that means that there are 25 unaccounted for. In other words, 25 do not like volleyball or basketball. So we want that for part C. Part A says, how many students like volleyball but not basketball? Well, these like volleyball, but these also like basketball. So for part A, we just want 55. Part B, how many people like basketball but not volleyball? These people like basketball, but these people also like volleyball, so take them out. Part B, we want 35. Part C, as we found, how many people do not like either of these sports? That was the remaining individuals for the 200. We found that to be 25. Note why this would make sense. If you add these numbers together, right, for regions 1, 2, 3, and 4, those are the only regions we have to work with. And the sum there, 25 and 35 for 60, 60 plus 85 for 145, plus 55 for the grand total of 200. A music teacher has surveyed 495 students. The results of the surveys are listed below. And note here, we got a lot more going on, because below it says 160 students like all three. So in this case, we're going to look at a Venn diagram containing 3 circles, right? And then we're going to answer our 3 questions below. So give you a moment here, if you need to pause the video and create your Venn diagram consisting of your 3 circles. So in order to answer this question correctly, we really want to consider creating a Venn diagram with the information given. Now this one's a little bit trickier, but the key here is to work with what's given to us in the middle first, and then work our way to the outside. For example, we were told that 160 students like all 3 types of music. Here in this case, a music teacher surveyed 495 students, and we're trying to determine how many like rap music, rock music, and heavy metal music. So I created a Venn diagram. I have rap on my top left circle for A, rock is my circle B, and heavy metal is my circle for C. So where they all intersect, A intersect B intersect C, is going to be 160 students like all 3. And then from there, we need to consider what else is given to us, right? 160 in the middle. So I sort of work my way to the top. And as I need to click, 245 students like both rock music and heavy metal. So rock and heavy metal. We have 245, but 160 of those are already accounted for. These like all 3. That means these 3 like rock and heavy metal. So for the 245 given to us, if we subtract the 160 in the middle, then that remaining 85 are those that like strictly rock and heavy metal. Then you have the 190 students that like rap and heavy metal. Rap and heavy metal. Now again, there's 190 that like both rap and heavy metal, but there's 160 that like all 3, including that. 190 minus 160 gives us the 30, just the 30, that exclusively like rap and heavy metal. Then you work your way to the top. 280 like rap and rock. Rap and rock, there's 280, but 160 are already accounted for. 280 minus 160 gives us the 120 that we need. Now, in order to find those that exclusively said they only like rap, they didn't like any other blend of music, just rap. Well, there's 320 students that like rap, but some of those like rap and rock, some of those like rap and heavy metal, and then some of those like all 3. How many of those exclusively only like rap? Well, 320 is what we start with, and we're going to take away all of those regions that involve rap. 320 minus 120 minus 160 minus 30 gives us 10 exclusively liking rap. For rock, 395, but we're going to subtract those 3 regions that are also in rock. 395 minus 120 minus 160 minus 85 gives us 30 students that exclusively like rock. Lastly, for heavy metal, right? 295 students like heavy metal, but we're going to take away the regions that are involved for heavy metal. 295, take away 30, take away 160, take away 85, leaving us with 20 students that exclusively like heavy metal. Let's answer the following 3 questions. Part A, how many students like exactly 2 of the 3 types of music, right? For 2 of the 3, we're looking at those numbers in that center region, right? These like all three, these like only 1 out of 3, these like 2 out of 3. The 120 individuals like 2 out of 3, that's rap and rock. The 30 individuals like 2 out of 3, rap and heavy metal. The 85 individuals like 2 out of 3, heavy metal and rock. So adding 85 plus 120 plus 30, for part A, we get 235 students. What about now for part B? How many like only rock music? Only rock, 30. Lastly, for part C, how many like only one of the 3 types of music? 30, 10, 20, for our grand total of 60. So for part A, 235 students. For part B, 30 students. And for part C, we have the 60 students. The slides will show us the diagram broken up, along with our breakdown for part A for our 235. For part B, examining to get 30. And part C, examining to get 60. At any time, please pause the video so that you can read through the sentence structure and how the explanation is done. There we have our example listed. Next example we want to look at is an example involving voting systems. It says here there are many types of voting systems. When people are asked to vote for or against a resolution, a one-person, one-vote majority system is often used to decide the outcome. In this type of voting, each voter receives 1 vote and the resolution passes only if it receives most of the votes. In any voting system, the number of votes that is required to pass a resolution is called the quota. A coalition is a set of voters, each of whom votes the same way, either for or against a resolution. A winning coalition is a set of voters, the sum of whose votes is greater than or equal to the quota. A losing coalition is a set of voters, the sum of whose votes is less than the quota. So again, the number of votes that is required to pass a resolution is called the quota. Do we reach that number or do we not? Sometimes you can find all the winning coalitions in a voting process by making an organized list. For instance, consider the committee consisting of Alice, Barry, Cheryl, and Dylan. To decide on any issues, they use a one-person, one-vote majority voting system. Everybody's vote is equal. Since each of the 4 votes has a single vote, the quota for this majority voting system is 3. The winning coalition consists of all subsets of the voters that have 3 or more people. In other words, right, if it's a 2-2 vote, it's split. There is no majority winning. If the voting system is 4-0 or 3-1, then there is a majority voting system, and therefore they reach the quota. We list these winning coalitions in the table below, where A represents Alice, B represents Barry, C represents Cheryl, and D represents Dylan. In other words, as long as you have at least 3 of the 4 in favor, you will have a winning coalition. In the event that you have only 2 or below, well, you're in a losing coalition. If Alice votes alone, then she is the losing coalition, as the winning would have B, C, and D. A weighted voting system, however, is one in which some voters' votes carry more weight regarding the outcome of an election. As an example, consider a selection committee that consists of 4 people designated by A, B, C, and D. Voter A's vote has a weight of 2, and the vote of each other member of the committee has a weight of 1. Notice now that the vote of A carries more of a significance because the weight is higher. The quota for this weighted voting system is 3. A winning coalition must have a weighted voting system, a weighted voting sum of at least 3. The winning coalitions are listed in the table below. Note in this case here that in some instances, a winning coalition does not need a majority vote. Because voter A has a larger weight, it carries a larger significance towards the sum of the votes. In this case here, a winning coalition could consist of only 2 people as long as voter A is in that coalition. Notice here that you do not get a winning coalition of BC, BD, or CD because a winning coalition of 2 must consist of A. However, even though A has a large vote, a weight of 2, note that BCD is one instance where A is not a part of the winning coalition. So it would have to be a majority vote if A is not involved. A minimal winning coalition is a winning coalition that has no proper subset that is a winning coalition. In a minimal winning coalition, each voter is said to be a critical voter, because if any of the voters leaves the coalition would then become a losing coalition. In the table that we just saw, the minimal winning coalitions are listed as follows, because if any of those, for example, if voter A and voter B vote together, that's a winning coalition. But if either of those two leave, then it is now a losing coalition. Likewise, B, C, and D is a winning coalition because it gets a point sum of 3. However, if any of those were to leave, that would then become a losing coalition. Right? Notice that A, B, C, D is not listed, nor is A, B, C, A, B, D, A, C, D. Because these, for example, if the voter that has a weight of 1 were to leave, Alice's vote carries such a strong weight that it would still be a winning coalition. So a minimal winning coalition is in the event that if one of the voters leaves, it becomes a losing coalition. We have an example. It says a selection committee consists of Ryan, Susan, and Trevor. To decide on issues, they use a one-person, one-vote majority voting system. Find all winning coalitions and find all losing coalitions. Keep in mind for number 1, if they are using a one-person, one-vote majority voting system, if there's only 3, then the majority has to be 2. So you must have a vote of 2 in order to get a winning coalition. Remember, that's our quota. So to find the winning coalitions consisting of Ryan, Susan, and Trevor, we will denote them as R, S, and T. We will go to the full screen. So we have R, S, and T, and it's a one voter majority. Everybody has the same point system. And so what are the winning coalitions? Pull back up the slide if we need to pause for a moment. Ryan, Susan, and Trevor, R, S, T. We just need 2. We need 2 for a winning coalition. Well, that means that R and S can go together, R and T can go together, but also S and T can go together, right? Those are each of our winning coalitions where we get a quota of exactly 2. No other opportunity. RS, RT, TS, and if we do anything else, we've already repeated it, it's the same thing. And then lastly, the winning coalition of getting quota of 3. That is RST. Right? These are our winning coalitions. What would the losing coalitions look like? Well, anything that's less than a 1. That is, a losing coalition would just be that if you voted by yourself and nobody voted with you. A losing coalition would consist of just R. Right? That's just a point of 1. That's not enough. A coalition of just S. That's just 1. It's not enough. Need 2. Coalition of T. And then there's that last example, right? Where if everybody votes in favor, well, then nobody voted, so a losing coalition, right? That goes to say that if nobody votes in one direction, well, that's the losing coalition. So not as much of a need to discuss the nature of that one there. We look at example 2. Example 2 then says, well, we have a selection committee that consists of 3 people designated by M, N, and P. So I'm going to go ahead and erase this here. Now I'll create a table this time because this problem is going to have a little bit more to it because we're going to have a weighting system that's a little bit different, right? It's not going to be one party, one person, one vote majority. So M, N, P. M, N, P. So it says here, M's vote has a weight of 3. N's vote has a weight of 2, and P has a vote of 1. The quota for this weighted voting system is 4, right? You got to have 4. You need 4 to win. right? You need 4 to win. So how can we do this? Well, can just any one person get it? That's our largest. But no, I'm gonna go ahead and go back to the full screen. Right, in this case here, a winning coalition can't just have one individual. We need 4, the largest is 3. But what if we put 2 of them together? M and N together? Because that's a score of 5, and we just need a 4. So that's good. What about M and P? Well, 3 and 1 is 4. All we need is 4, so that's a winning coalition. M and P. What about N and P? Can we put just those 2 together, right? 2 and 1 is 3. We need 4. That's a losing coalition. Maybe we can go ahead and start listing our losing coalitions as well. So every time we can't find something that works here, we place it here. That is, nothing can win by itself. We just found that N and P cannot win together. Using semicolons as commas because we have commas within the sets and it gets messy, so we can use a semicolon to separate things that already have commas inside of them. What else, right? So we've exhausted all the possibilities of using 2 things. Let's go to 3, right? All 3 of them together, M, N, and P is a score of 6. That works out. One, two, three, 4, 5, 6, 7, and that last one, of course, is the empty set. Just reminding ourselves that when you have 3 of something, how many ways can we combine 3 of something? Well, again, 2 to the 3rd power. We either include something or we don't. 2 cubed is 8. 1, 2, 3, 4, 5, 6, 7, 8. Right? Either you include something or you don't. You have 2 choices. You have 2 choices on 3 different letters. So if you have 2 choices on 3 things, 2 times 2 times 2, giving us 8 total options. So there are our losing coalitions. Here are our winning coalitions. Now, are there any of these that are minimal for number 2? Right? That is, it just says find all winning coalitions, but can we determine the minimal winning coalitions that we just found for our example? What can we come up with there? Right? If you take one of them out, that it's no longer a winner. So for number 3, minimal winning coalitions. Well, go to the full screen. M and N together is 5. If I take out M, I'm at 2, no longer a winning coalition. Likewise, if I take out N, I'm at 3, no longer winning. But it's just one example. If I take out any one of those items, do I go from winning to losing? Yes, MN is a losing coalition. If I take one out, therefore it's a minimal winning coalition. You don't have to worry about these. They're already losing. This is the example of going from winning to losing if I take something out. MP, well, again, that sum is 4. If I take out 3, I'm down to 1. Likewise, if I take out 1, I'm down to 3. That's losing. So once again, MP is a minimal winning coalition. Now, give you a moment here to think about this last one here, MNP. You stop the video if you need to. We'll go back and look at that definition once more. I will pull back up the full screen. Right? A minimal winning coalition is a coalition that has no proper subset. That is a winning coalition. In a minimal winning coalition, each voter is said to be a critical voter, because if any of the voters leaves the coalition would then become a losing coalition. So once again, right? You would think that maybe we would have an example that we wouldn't have to worry about. But even in this example here, I'll go back to the example. Even our last example, MNP, right? If I take out M, I no longer have a winning coalition. If I take out N, it's no longer it's still a winning coalition, but it's just the fact that M is the critical voter in this case. If I take out M, this is no longer a winning coalition. So once again, it's a minimal winning coalition. Following exercise, use the given information to find the number of elements in each of the regions labeled with a question mark. So again, with 8 regions given to us, right? If we're taking 3 sets and placing them in a Venn diagram, we have 8 regions to consider. In this case here, we're being given some information about our two sets, or rather our three sets, A, B, and C, the intersection of A and B, and then the number of elements that are in our universal set. So can we find our remaining information? Give you a moment to pause the video, see what you can come up with here. And I will do the same as I create my Venn diagram and look to fill in the blanks. If we're looking at this here, one of the key things is the number of elements that are in A intersect B. Remember that A intersect B, according to our image here, are these two spots. Well, we're already given the 3, so that means that 3 out of our 15 are here. So the remaining 12 must be in this location here. And I'm going to go to the full screen. Again, think about where I got 12. We were given that 3 is located here. We're told that the intersection contains 15 elements. So there are your 15 elements now. If A contains 28, well, look right here, right? 12, 15, 22 of the 28 are already here. So the remaining 6 go in this location. For B, we have 31. 12, 15, 20 of the 31 are already presented. So the remaining 11 are on this outside. Then we go down to C. 7 and 3 for 10, 15. 15 of the 40. So the remaining 25 are here. They tell us that the universal set has 75 elements. Well, if there's 75 elements altogether, we've already accounted for all of the 7 regions in A, B, and C. So region 8 is going to be 75 minus all these numbers. Let's find that out. 6, 12, 11. 6 and 12 is 18. Plus 11 is 29. 34. 37, 44. 69. 75 minus 69 is 6. So there you go. We have found the number of elements for each of our 8 regions based upon the given information here for exercise 17. We'll take a look at the example on the right, number 18. Given the information, we want to find what is unknown here. Now again, what you want to consider is trying to work with whatever's clustered, and in this case here, take a look at the set for C, right? If you look at C, C has everything but region 1, right, where they all intersect. And you take a look there and see that if they tell us that the number of elements for C is 1,000, well, then I have just about everything accounted for, except for that one thing, right? That is, if I take 1,000, the number of elements for C, take away 780, take away 94, take away 110, I'm left only with 16. So 16 is the intersection. But now that I have found the intersection of 16, I have everything that I need to find the remaining region for A, everything I need for the remaining region of B, and thus I can find everything on the outskirts, given the number of elements for the universal set appears to be, 2,900? So now we'll find the remaining elements in A, given the fact that the number of elements for A is, 610. Should have written this out first. So 610 minus the 310 that's going to give us the 300 minus the 16 minus the 110, 174. For B, once again, they tell us 440. So I'm going to start with 440. I'm going to subtract the 310, subtract the 16, subtract the 94. We'll have 20. So now we have all 7 regions accounted for within A, B, and C. We just need region 8, all of those elements that are in the universal set that are not in A, B, or C. So we're going to take the 2,900 given to us, 2,900. We'll subtract each of these numbers. Subtract 174. Subtract 310. Subtract 20. Subtract 110. Subtract 16. Subtract 94. Subtract 780. The remaining number, 1,396. All right, remember to think about what that number is right there, right? Every number on the outskirt in region 8, well, if you take A union B union C, right, everything that's in A or B or C, that's all these numbers right here, all right? That's the number that we just subtracted away. And the complement of that is 1,396. So it's all those that aren't in A or B or C. Have an example involving financial assistance. A college study categorized its seniors, juniors, and sophomores who are currently receiving financial assistance. The types of financial assistance consist of full scholarships, partial scholarships, and government loans. The following table shows the results of the survey. It says here, find the number of students who are currently receiving financial assistance in each of the following sets. So for example, right, part A says S intersect P. Well, what we're looking at here are the seniors who have partial scholarships, right? What is that number where S and P intersect, right? And if you look at the table, all you're essentially doing is taking the row for seniors and the column for partial scholarship, and you see there that number is 175. Part A, 175. Now we're going to find the remaining examples through F, B, C, D, E, and F. Part B says J union G. Well, how many juniors do we have? And then how many government loans do we have? But you got to keep in mind, right? We're looking for a number, right? Find the number of students. And we had a formula before, right? And that formula tells us here that if you have an overlap, you have to subtract the overlap. The number of students, if you look at part B, right, they want to know a number of students. So in part B, it's the number of juniors union government loan. And according to our formula, we want to find the number of juniors, add it to the number of students that receive government loans, and subtract the intersection. Subtract the number of students that are juniors and are receiving government loans. Because if you just add these two numbers together, you're going to add the same number twice. Consider, how many juniors do we have? The totals are at the end for juniors. 180 are on full scholarship, 162 are on partial, 110 are on government loan, and there's a total of 452 juniors. Likewise, for government loans, there are a total of 386 students. That is 190 seniors, 110 juniors, 86 sophomores, for a grand total of 386 receiving government loan. Now think about why we're about to subtract this number in a second. We're going to subtract the intersection where J and G intersect, and that's 110. The reason why we are subtracting 110 is because 110 is included in the total of 452. 110 is included in the total of 386. We added it twice. Because we added it twice, we need to go back in and subtract it once, which is what the formula tells us to do here. So we're going to add our first two numbers, 452 plus 386, to get 838, and subtract 110 for part B, 728. Give you a moment here to now pause the video and see how many you can come up with, and we will work through each of them together to find our answers. Part C is asking us to find the number of students that are sophomore or not on full scholarship. So think about what F prime means. F prime means that you're not full, which means you're either partial or your government loan. So using the formula from before here, if I want to find the number of elements in M union F prime, I want to find the number of elements in M, add it to the number of elements in F prime, and subtract the overlap. Subtract the number of elements that are in M intersect F prime. We'll come back to this. Number of elements that are sophomores, the number of sophomores we go across, we get 326. The number of those that are not on full scholarship, well, again, if we look at our table for the full scholarship, there are 504. Now think about how many there are on scholarship or getting government loans. 504, 463, 386 for a grand total of 1,353. So if you're not full scholarship, you're not 504, then you're the remaining 849. Lastly, we're going to subtract the overlap. The sophomores intersect those that aren't on full scholarship. So we're not looking, right? If you look at that, M intersect F is 114. But we're not looking at F, we're looking at F prime. So we're not concerned about M intersect F, we're concerned about the other two options. F prime means P or G. So M intersect P is 126. M intersect G is 86. These are the two numbers that come from this. If you're intersecting not F, that means you're intersecting P or you're intersecting G. And I get two numbers that I had to subtract from this overlap. So now we're going to add these two numbers and subtract the sum of these two numbers. 326 plus 849 gives us 1,175. But from there, we're going to subtract the sum of 126 plus 86. I put 126 and 86 in parentheses and then subtract. We get 963. With part D, we have S intersect FUP. And once more, we take a look and we see that in order to find the intersection, we first find the union. I'm going to write out here, S intersect FUP. So to find the number of elements in the union, we'll do the formula once more. FUP, by U I mean union. So number of elements for F plus number of elements for P minus the intersection F intersect P. We go to the table. Number of elements for F is 504. Plus number of elements for P, we have 463. Minus the intersection. Notice here for F and P on the graph, they don't intersect. They're mutually exclusive. There is no overlap. This number is 0. And subtracting 0 doesn't change anything. So here's the example of having two mutually exclusive or disjoint sets. Either you're on full scholarship or you're on partial. There is no overlap. Add 504 to 463. 4 plus 3 is 7. 0 plus 6 is 6. 5 plus 4 is 9. So that's how many we have here, 967. Now, how many of those are intersecting with our S here? In this case, our seniors. So to be able to work this out here, now it's nice to have the number, but now let's consider going to the table, right? If we can do that, we're going to try to do that. We have a formula from the last section. We're intersecting over a union. We're going to distribute here. S intersect F or S intersect P. How nice this is going to be. What's the intersection for S and F? Where's the overlap for S and F? What's 210? What's the intersection for S and P? Well, for S and P, the intersection is 175. We're going to union or bring these two together, and there is no overlap, so we're just going to add them directly together. 5 and 0 for 5, 1 and 7 for 8, 2 and 1 for 3, giving us our grand total here of 385.